Okay, let's get it started. So, good morning, everybody. Um, let's share my screen. Could you see my screen?
Yes.
Yep, sure
Oh,
can.
great. Yeah. Uh, you know that we started Transformer chapter. Uh, Last class, we looked the working principle uh, and then followed by some numerical example. Today, we will be looking Transformer equivalent circuit. This means how we can represent a transformer. What is its equivalent circuit? And inside the equivalent circuit, you will notice that there are several parameters: resistance, reactance, etc. So we want to find out those parameters. And to do that, we have to conduct two tests. One is called open circuit test, other one is called short circuit test. So I will be explaining, and then we will be looking some numerical example. Also, we will be calculating transformer efficiency, voltage regulation, and then we will be discussing transformer types. So these are the points that we'll be discussing today. The first of all, that transformer equivalent circuit, everybody see this one. You see the middle portion. Until last class, like we were discussing the ideal transformer, and always I just drew there is a primary coil and there is a secondary coil. So, and then we call it ideal transformer. But today I am showing you this one. This is the real transformer, and this is the equivalent circuit for a actual transformer. So this means that if you start from left side, we are applying voltage on the primary coil and current flowing, which is ion on the top. And I am assuming two components. One is, you see, R1. So R1 means there is a small resistance inside the coil, inside the primary coil. And of course, a coil is mainly the inductance. So it has inductive reactance. So that's why that is represented Jxn. So this means in the primary side, the equivalent impedance is R1 plus Jxn. That is the meaning. So I am coming this portion later, and then see right side, secondary voltage is V2 and current flowing is I2 if the load is connected. That is the meaning. And then you see I have represented by R2. R2 means resistance of the secondary coil. Similarly, Jx2, its reactance, because there is inductance, and transformer has frequency, so X means 2 pi FL. So that's why there is extra. And then you see this portion basically represents the magnetic core on which the coils are placed. So you remember I was drawing a rectangular body which I called magnetic core. On that magnetic core, left side and right side coils were placed. So the thing is that once you apply the voltage on the primary and then current it starts flowing, then first voltage induced in the primary coil, it produces current, then it produces flux, and that flux start flowing through the magnetic core material. Now once currents flow through the magnetic core material, there are some losses inside the core material itself. Those losses are not related to the coil magnetic material. Therefore, to represent that one, here you see the arrangement: RC component and in parallel XM component. So in the next slide, I think I have explained this one. Everybody see? In transformer, there are two types of losses. One is called copper loss, which is called variable loss. Other one is called core loss, which is treated as constant loss. So this means that depending on the magnitude of input current or output current, and depending on the resistance value, that copper loss will be varying, can be variable, because copper loss is I square R. So as I showed you in the picture here, there is iron. So how much is the iron? So iron square iron, that is called copper loss. Similarly, on the right side, I2 square multiplied by R2, that is the copper loss on the secondary side. But I am using another term which is called core loss. It is constant. So therefore, it does not matter what is the amount of primary current or resistance. There is some constant loss. If you apply any voltage on the primary, magnetic material will be excited or magnetized. Consequently, there is some constant loss. So those constant loss has two components. One is called eddy current loss, other one is called hysteresis loss. And you see, I have written down that eddy current loss is proportionate to frequency squared, and hysteresis loss is proportionate to frequency. Therefore, hold on for a moment here. Let me show you on the whiteboard, then it will be fine to you. So I am talking about this core material, magnetic material, on which we place the coils. For example, like this side is our primary and then this side here. So once we apply the voltage here and then current flows, and then you know that we discussed the flux is created. So this is that flux. Now the thing is that this material, that rectangular or square body, uh, what happens when this flux flows inside the core material, because these are the magnetic material, and you see this flux is flowing, so they create some sort of current, they create internal voltage and internal current, and those are circulating in nature. For example, one current is flowing here locally, other current is flowing here, some current is flowing here. Those are called the circulating current. That is the meaning of the word AD. EDDI. AD means circulating current. So therefore, I mean, flux is flowing in that way. That is fine. But at each and every point inside the magnetic material, some sort of current is being developed, which is called eddy current. And you know, because there is current flow, so there is some sort of loss. Okay, this magnetic material has also a small resistance, this magnetic material itself. I'm not talking about the coils. I'm just talking about the magnetic material, property of the magnetic material. And then because this flux is getting changed, flux is alternating this flux, and this is magnetic material. So because of the change of the magnetic property like North Pole and South Pole, there is another small loss which is called hysteresis loss. This is that word. Hysteresis, it is called. So this hysteresis loss is due to magnetic cycle change. So therefore eddy current loss and hysteresis loss, these two are the internal due to the magnetic material. So that's why whatever you connect any load on the secondary or not, it does not matter. Once you apply the voltage and if current flows on the primary, then this core will be excited, and then there will be those two losses, hysteresis loss plus eddy current loss. So just keep in mind that is the magnetic material property or the core material property. So therefore that thing I was showing you in that slide. Now come back. Everybody see this one. losses in transformer. Copper loss is due to resistance, that you easily understand, and which is variable loss because that is I squared loss. But constant loss, which is the core loss, that is coming from the magnetic material. And after a lot of experiment, it has been confirmed by the power engineers that eddy current loss is proportionate to frequency squared and hysteresis loss proportionate to frequency. So this means that if you apply voltage or current to the transformer primary, and that current or voltage had lots of harmonics or lots of nonlinearity, then the frequency will be much higher. Consequently, there will be much eddy current loss. So that's why it is not desired that you will apply non-sinusoidal signal or harmonic prone current to the primary of the transformer. You should provide only the pure sine wave to the transformer so that there will be less eddy current loss and hysteresis loss. Anyway, so everybody, I mean, from today, keep in mind that in a magnetic material or in a transformer, there is all loss, which is called core loss, and core loss has two components: eddy current loss, hysteresis loss. Now, to represent this core loss in the equivalent circuit, this is the portion. Therefore, as we already discussed, that R1 JX1, this is related to primary coil. R2 JX2, this is related to secondary coil. But this portion is related, or this portion represents that core loss component. So therefore you see what is happening. You are applying voltage, this means current ion is flowing, that is fine. And then I2 prime, that current is going actually to the coil. But then this portion is representing that magnetic core material. You see, I have given the name I subscript A, and it has two component. One component is IC, other component is IM, and I have placed them in parallel. So IC represents that core loss component, and IM, that is the magnetizing current. This current is actually magnetizing that material, and this portion is going just as a loss. Therefore, to represent this core loss, this is that portion, because this is loss, so you can treat this is just I square R. So that's why this I current, excitation current, or additional primary current, that is causing the loss through this path, and this is actually magnetizing. That's why you see I have explained this thing. If you see the book equation number 4.46, that I has two component, IC plus IM, and I have written for you. I is excitation current or additional primary current needed to develop the resultant mutual flux. This is the I, and it has two parts, IC, IM. What is IC? IC is core loss component of the excitation current that is supplying the eddy current and hysteresis loss in the core. And this IM is the magnetizing component of excitation current needed to magnetize the core. Because if you don't magnetize the core, then there will be no voltage developed in the secondary side. Consequently, you will not get current secondary side. That's why you need this one. But this portion is just going as a loss inside the magnetic material. And then I have written this one, you see. IC is in phase with E1, but IM lags E1 by 90 degrees. This means if you see the picture, E1 is that excitation voltage of the primary coil. And you see, because these all are parallel, but this is resistant, so you know the property of resistance, the relationship between voltage and current. So IC is in parallel, sorry, this is parallel this one. This means this current and voltage is in parallel. They have no phase difference. But because this is inductant, So IM current will lag this voltage by 90 degree. That is the meaning, that thing I have written here. So therefore, I mean, you might be asked these questions in the midterm exam or final exam, that draw the equivalent circuit of a transformer. Then everybody, please, you will be drawing this circuit. I mean, including this magnetic branch or the magnetic material property. Yeah. Everybody, could you follow me?
Yeah,
Yes,
makes
sir.
sense.
Okay, great. Now, everybody say, actually, this is lab number 2 that you will be doing in the lab. So, I mean, you know that this week you will be going to the lab, but this week it will be just the orientation. The lab TH will explain you about the safety rules. They will show you the motor, generator, transformer, those components, apparatus, devices. But actually, from next week you will be doing the lab. So next week you will be doing the first lab about three-phase circuit, and then the second lab will be in, I mean, another week, exactly this thing. So what you have to do, you have to find out 6 parameters. Everybody see, R1 is one parameter, X1 is another, R2 one, X2, RC, and XM. You have to find out these 6 parameters, and this is very very realistic condition. In real situation, you have to find out those 6 parameters. I mean, in a real manufacturing company, once transformer is built, then the first test goes to check that, okay, those 6 parameters make sense. Those 6 parameters, once again, this R1, X1, R2, X2 value, RC value, and XM value. Now the thing is that how to measure those things. What test do I need? That thing I am going to discuss. So therefore, that is the subject matter both in this class plus in the lab. So therefore, if you now properly follow me, listen to me, then like you all will be done the lab 2. Easily you can do lab 2. Okay, so moving forward. So to find out those equivalent circuit parameters, I will be doing 2 tests. One is called open circuit test and other one is called short circuit test. And I have written down here that open circuit test provides core loss. Short circuit test provides copper loss. So I am coming those points on. Before starting, so I think I need to tell one more thing. Hold on. Okay, let me delete all of these things. Okay, so sometimes, I mean, although I showed you the equivalent circuit of transformer, that big diagram, but sometimes in the job market, you will be asked, can you simply draw the transformer equivalent circuit? What is the simplest form of the transformer equivalent circuit? So therefore, your answer would be simply a coil. This is the equivalent circuit of transformer. So you understand, simply you will be drawing a coil. That will be the smartest answer. That will be the most intelligent answer. So therefore, how to do that? So therefore, let me come back. I'm briefly coming that point. Uh, I'm just quickly showing this thing. Okay, and so you have that primary here, and then you have that secondary, and okay, these things. Here you had that V2, this was R2, and then this was X2. Sorry. This is R1 and then this is X1. This is RC and then this one is X1. Okay. So my goal is that how I can conclude from this diagram, how I can reach from this diagram to that simplest form that I am showing you. So what you will be doing, first you will be transferring this to R2X2 referred to the primary side. You know, in the previous class, last class, we were discussing how we can transfer the impedance from the secondary or load side to the primary side. You remember we did like A square multiplied by GL. We multiplied by turn ratio. So the first step is that you transfer these two components on the primary side. That is the very first task. So how you can do that? You will be just multiplying by turn ratio square, A square multiplied by R2. That will be your new representation of this if you transfer this on in this side. Similarly, for this on A square X2, you can do that. So therefore, if we do that, just I am deleting all of these things. So therefore, it will look like that. Okay, and then I just transferred that thing. This one was that RC and this one was that XM. This one your R1 and then this one's your X1. Now this one is this one. A square R2 and then this one is this one. A square into X2. This means now I have transferred everything from secondary side to the primary side. And what I did, I have moved this portion, magnetizing core portion or magnetic material portion at the leftmost side. This is the assumption. This is the approximate equivalent circuit. Okay. Next time, what you do, you sum up R1 with A square R2 because these two are the resistance and you sum up this one with this one. So if you do that, so therefore, for example, here you are getting, if I take that on R1 plus A square R2. So this means that this one is, you can give the name that this one is my R equivalent because I summed up this one. So therefore this thing done, sorry. This was the resistance and then this one. So I will sum up this one with the previous one. So therefore X1 plus A square X2. This means I took that on there. So now let me delete these things. Now let me all of these things, this one also. So therefore picture will look like this. Everybody, could you follow me what I am saying? Therefore this is X equivalent. I mean, I transferred everything from secondary side to the primary side and I got resistance equivalent, R equivalent value, R1 plus A square R2. A is the turn ratio. A is that V1 over V2 or N1 over N2. That is my definition of the A, turn ratio. Okay. So now so far I got this one. And then you see, as I told you that I moved this on, this represents the magnetic core, but in real practice that core loss is actually very negligible. It is not that much, only like 3% or 4% of the total capacity of the transformer. So therefore, you can neglect this portion. I mean, in real practice, it will be there, but percentage is very low, so you can neglect. So therefore, now in the circuit, what is remaining? R equivalent and X equivalent. Only these two things remain in the circuit. So now you see, transformer means basically the coil. And what is the meaning of the coil? Coil means mainly inductance is dominating, mainly reactance is dominating. So therefore, in real practice, if you compare this one with this one, their magnitude in real practice, this is very, very large than this one. This means x1 plus a square is much larger than this one. So in that sense, you can neglect this portion. No, I don't need this one. So therefore, ultimately, in the circuit, only you will have that X equivalent. So in that sense, I told you that if you are asked that what is the simplest form of the transformer equivalent circuit, simply you will be drawing a coil. That is the transformer equivalent circuit. So everybody, could you follow me what I explained?
Yeah, makes sense.
Yeah, yes, yes. You will be just remember this is the like smartest answer or the most intelligent answer. Sometimes in the job market, like you are discussing with your boss and they may ask you one tricky question. Say, hey, do you know the simplest form of transformer equivalent circuit? The answer is yes, I do know. And then you will be drawing simply a coil. So that thing I explained you that how you can represent transformer with the help of a single coil only. Yes. Okay, now you understand that thing, and then once again a little bit. So therefore here I had that R1 plus uh, A square R2. So and then I said this one is that R equivalent. So therefore this one is R equivalent and this one is X equivalent. Now if I want to represent in the format of impedance, so I could write in that way Z equivalent, I mean in the impedance format, so that this R equivalent plus J, this one X equivalent. So everybody will be remembering this format. So this is the Z equivalent of a transformer, R equivalent plus JX equivalent. And what is the R equivalent? R equivalent is this one, R1 plus A square R2. This is R equivalent. And then this one is your X equivalent. So therefore these two things, x1 plus a square x2 equals to X equivalent, we will be utilizing this one, this equation to calculate some numerical problem. Same thing, we will be utilizing this on R1 plus A square R2 equals to R equivalent to calculate problems. So everybody just keep in mind. Okay, now again going back there. So we want to conduct two tests. One is open circuit test and other one is short circuit test. And then followed by that, once we understand those two tests, how to test and how to find out the equivalent circuit parameters, then we will be able to solve this type of numerical problem. Therefore, I mean, exactly you will be getting this type of data in the lab number 2. Like for example, say, consider a 15 kVA 7500/480 volt 60 hertz distribution transformer. Assume that the open circuit and short circuit tests were performed on the primary side of the transformer and that the following data were obtained. You need three things. You need on voltmeter, ammeter, and wattmeter. And you will be getting two sets of reading. One is based on open circuit test, other one is based on the short circuit test. And then based on this data, determine the parameters of the approximate equivalent circuit referred to the primary side. So for example, we have these three data and another three, total 6 data. With the help of this data, this voltage, current, and power magnitude, you can calculate those 6 parameters of the approximate equivalent circuit. This means value of R1, R2, X1, X2, RC, and XM. Those 6 parameters. So now, before going to the problem, again I will be showing you how you can conduct those two tests, and I mean why I said these things. So therefore, once again, let me take you there on the board, so then it will be clear to you. Let me clean off all of those things. Okay, so first let's go with the short circuit test. Okay, first we will be discussing this one, short circuit test. So for the short circuit test, what you will be doing, uh, you will be adding a ammeter in the primary. Of course, at the beginning, you will be connecting a voltmeter, and you will be connecting a wattmeter. This is the wattmeter, and then this is transformer primary side, and this is transformer secondary side, and you will make the secondary side short. This is the short. This means secondary side. So accordingly, it is called the short circuit test. So everybody says, so what is the experiment? What is the test? You are applying the voltage at the beginning, and then that current is flowing, which is that ion current is flowing. And this is and you are conducting your test on the primary side. This is the secondary side. Secondary side is short. Secondary side is short means uh, this side is LV, low voltage side. This side is high voltage side. You know, in the lab, you will see that in a transformer, although our transformer is not like very high rating, or it does not have very high value, a small size of transformer, but one side has high voltage, other side has low voltage. Because you are making short, definitely you will making short the low voltage side, not the high voltage side. So you will conduct experiments on the high voltage side, primary side. So, and because you are making the short circuit, so what you will be doing, you have to careful about this ammeter reading, so that it does not exceed. Now you will be getting three reading. This rating I am giving the name VSC, V subscript SC. SC refers to short circuit. I am giving this current name ISC, and this is the wattmeter. You know, the wattmeter means it has this CC, current coil, and this coil is called the PC, potential coil. You know, wattmeter has two coils. This coil measures the current flowing, and this coils measure the voltage. Accordingly, it is called CC and PC. And this is wattmeter, and let designate the rating of this one by the symbol VSC. Therefore,
For the emitter, did you say we needed to be careful to avoid exceeding its limitation? Is that what you said?
yes, exactly. I'm again coming that point. So for this test, everybody see, for the short circuit test, most important thing, you will be looking this ammeter. For example, in the lab, probably you will be using a 50 ampere rating ammeter. From the beginning, like you will be noticing that this current does not exceed this value. Because you have made the secondary short, it is the short circuit. So easily like this current value jumps. So therefore, what to do that, what you will be doing, actually you don't need to apply the very high voltage here. From the beginning, you will start only like about 2 to 12%. I mean 2% to 12% of the rated voltage. For example, the rated voltage is 120 volt here. So you have to use a what is called that variac. There will be device here. this edge. Like this is 0 volt, then this is 10 volt. Gradually it will increase. Let's say here it is 50 volt. Sorry. Then in that way it will be like 120 volt position. So there will be the knob setting. You will go in that way. You just adjust. But what I said, you will at first you will keep this voltage at the 0 position. You make the whole connection, but you keep this in 0 position, that knob setting. This is called the variac. Uh, this device is called the variac, which will be connected at this point. Yeah. So therefore LabDA will show you how to connect that. I think already they have made 3 videos and I have uploaded those on the lab section. So you can see the lab, what thing I am talking. This is called the variac. So with the help of variac, you will gradually increase the voltage. This means variac is a variable transformer basically. It can increase or decrease the voltage. So initially you will be setting your this voltage at the 0, and then gradually you will increase the voltage. And as I said, typically 2% to 12% of the rated voltage. This means of this 120, you will notice that this ammeter has reached its rated value. That thing I am telling. Therefore, it is not like, okay, you quickly jump, you will go 120, by then this ammeter will be burnt, your transformer will be burnt. So that's why for the short circuit test, after connecting the circuit, after making the circuit, the first thing is that you concentrate on this ammeter and very slowly you start increasing this variac. Little you apply voltage and go until that maximum point. Don't exceed that point. Once you reach that point, then you disconnect this one. You don't apply the voltage. Your test is done. I mean, it is very simple. I mean, in 1 or 2 minutes, you can do this test. Just you have to make caution. You have to be careful so that this ammeter does not exceed the rated value. That is the thing. So therefore, once you done that one, then you are done. You got 3 rating: VSC, ISC, VSA. You will just take these 3 rating, nothing else. Everybody, could you follow me so far?
Yes.
Exactly. And you see, I am not sure whether you have noticed or not. I already uploaded all the lab. You will be doing 8 experiments already. I think 2 days before, I already uploaded all the lab experiment description on the lab section, eCourseware. You will be seeing experiment 1, experiment 2. In that way, I already uploaded. So there again, you will get these explanation in detail and the diagram. So now I explaining as part of the, the class lecture or the class part. And also I uploaded 3 videos that the lab TH have made. For this week on, it is called Introduction to Energy Conversion, the video title. And then there is lab 1 and lab 2. And then very soon we will be uploading all of the labs. Currently the TAs are making the videos. So therefore, if you read that experimental description sheet, experiment 2, then you will be getting detailed description about this. Okay, so therefore, everybody see, from this test, you got 3 rating: VSC, ISC, and VSC. And then I am just removing this side. I just want to keep those ratings. Okay. Only you have these 3 rating: VSC, ISC, VSC. Now, what you will be doing with these 3? Now, you remember that equivalent circuit I was showing you? You have to find out G equivalent, which is GSC, because we got from short circuit this one. So what is this one? GSC or G equivalent? VSC over ISC. So right, because impedance is voltage over current. So what is this rating? This is this value, the value that you will be getting during the experiment. What is ISC? This one. Now, what you have to do, I must recommend you, you please consider the phase angle, which is theta SC. And you see why I put the minus sign? Because this is transformer, and you notice that transformer equivalent circuit simply a coil. And what is the coil? What is the type of the power factor? Is it leading or lagging? This is lagging because this is coil. So in case of transformer, power factor is mainly the lagging. So to represent that lagging power factor, I put a minus sign here. Now the question is how to get that angle theta. How you will get? So can you guess how you can get from these three rating? You have VSC, wattmeter rating, you have ISC, you have VSC. So what you can do, everybody say, I am writing the equation VSC, then VSC multiplied by this ISC multiplied by cosine of theta SC. I think now you got it. You understand? V equal to VI cos theta. Therefore, from here, and you know all three ratings. Only you need three rating, nothing else. And then from there, you find out cos theta SC. And finally, you put that theta SC value here after calculating from here. Do you get it? Okay. And then after that, once you do that, and then move forward. So you are calculating G equivalent. So this means your G equivalent is, you can put that in the numerator. So it will be like positive. So whatever VSC IC, you will get a magnitude. For that magnitude is K. And then take that angle in the numerator. So it will be positive theta SC, positive angle. And then this means it has two components. You can say this is R equivalent plus J equivalent, Jx equivalent. Everybody say this is in polar form. This is a phasor. This is a vector. And this is G equivalent. From here I got this one. And now you convert into rectangular form. So in the rectangular form, you can say first part is the real R equivalent and second part is the imaginary part, Jx equivalent. So and then now come back. What is that R equivalent and what is that X equivalent? Now I am deleting this side and these things. What is that R equivalent? So we discussed before. So your R equivalent that R1 plus A square R2. You remember that equivalent circuit that I was discussing, that I transferred R2 from secondary side to the primary side. This is your R equivalent. And what is your X equivalent? So X equivalent was X1 plus A square X2. This is your X equivalent definition. So therefore, once you get these two values, then write down this one. What is your goal? Your goal is to find out this one, R2, X1, and X2. This means from this short circuit test, you will be able to know these four parameters, R1, R2, X1, and X2. So now, and then of course, A is the turn ratio. Definitely you will know what is the turn ratio of the transformer. So now how to do that, how to calculate this one? So now you have to make some approximation. I'm deleting this line. You have to make some approximation for a well-designed transformer. If a transformer is designed well, pretty well, or in a good shape, then this is the approximation. Like R1 equals to A square R2 which is, I mean, pretty close to R equivalent over 2. You have to make this assumption. So therefore, this is true for a realistic transformer. As I said, for a realistic transformer and well-manufactured, well-designed transformer, this thing's true. This holds for. This means what I said, this is your expression. You are getting R equivalent value from here. You have a value and you need to know R1 and R2. That's why you will make this approximation. R1 equal to A square R2, which is almost equal to R equivalent by 2. So this means first you are getting R1, whatever. For example, R equivalent is 50, then 50 over 2, 25. So directly R1 is that value. So you are getting R1 value. And then how to get R2 value? Again, A square R2 equal to that number, and A is the turn ratio of the transformer. That you will be given. So then you are getting R2. So then exactly the similar way for a well-designed transformer, that X1 equal to this one, A square X2, which is very close to this one, X equivalent by 2. You will be using this one. So then from here you will be getting X1 value and X2 value, similar to that method. So in that way, from those three readings, only like VSC, ISC, and VSC, you will get those 4 parameters of the transformer. Could you follow me?
Yeah, makes perfect sense.
Okay, great. So, I mean, again, soon I will take you a real example, then you will get more fun. Just now I am discussing you the theory. I am deriving the equation. I'm just explaining how to do that in terms of theory, but then soon I will take you the numerical example. Then once again, you can recap this knowledge. And then I'm saving this one. Now I want to discuss, I already said this is fine. Now I want to discuss the open circuit test. You see, we got 4 parameters, R1, R2, X1, X2. Now 2 parameters are remaining, RC and XM, that magnetizing or the core material, those 2 component, sorry, those 2 parameters. So I have to conduct the open circuit test. Now I will make the open circuit test. So let me get the title. This is open circuit test. So what you will be doing, again, the similar things. Exactly the same process. This time you will keep secondary side open. So this time, this side is your HV side, and this side your LV side. And, oh, sorry. This is actually that wattmeter. After that, there is that primary coil. And then this one is your secondary coil. Yes. Okay. And again, you need on voltmeter here at the beginning. Okay. So here you are applying the voltage V1, and then current flowing is this on ion on the primary side. And as I said, this time, this side will be high voltage side. You will keep it open, and you will be applying the voltage. I think I already wrote on the low voltage side. Now, again, this you will get 3 reading. This one is, this time you will give the OC to indicate open circuit. The voltmeter reading will be VOC, open circuit, and this is wattmeter. Wattmeter reading you will designate by POC. Okay, in this test, you see, now because this is open circuit test and you have kept high voltage side open, so you are not that much risk. This time on the primary, you can apply the rated voltage, no problem, because secondary is open circuited, so this current will not go high easily. But still you will be looking this ammeter, but typically it is not a problem always. Just you have to apply the full rated voltage. You have to go until 120 volt. In this case, you go the full voltage, still you will be set. And then once you get the full voltage and you took these three reading, VOC, IOC and VOC, then you are done. And once you get that on, then now you start the calculation. So what you will be doing, what will be your calculation? You see, in this case, my goal is to find out that on probably, if you remember that equivalent circuit, I had RC here and I had XM here, that magnetic branch. If you remember, I had XM here and I had RC here. Now with this test, I want to find out these two components, RC and XM, core loss resistance and then magnetizing reactance. That is the goal of this test. And because they are in parallel, that's why this time I will be calculating the admittance instead of the impedance. So what I will be doing, now I am cleaning up everything. I only will make available those three ratings. I have these three ratings, IOC, POC, VOC. Now what I will be doing this time, I will be finding Y, admittance, YOC. What is the meaning? So you all know the definition. Y means IOC over VOC. Could you remember, everybody? Y is the admittance, not the impedance. So admittance is current over voltage, not the voltage over current. Like when it is impedance, that is V over I. But once it is admittance, Y, it is the reciprocal, Y equal to 1 over J. I think now you can remember. Y is the admittance, which is IOC over VOC. Therefore, you got those two readings. And then again, you need angle here. You have to consider the angle. And then again, this will be the minus theta OC. This is that power factor angle. So how we will get, and I put the minus sign because once again, this is transformer. Transformer has always lagging power factor. So I put the minus sign here. Then how we will get that angle theta? Again, utilize the similar to the previous case. So VOC, that VOC multiplied by OAC, and then cosine of theta OC. Therefore, from here you calculate the theta OC and plug in that theta OC there. And then what you will be getting? So this will, you have to divide IOC over VOC. So you will be getting GOC minus, because I mean, you will get one number and then this is minus, or and then convert into rectangular form, GAC minus J BM. I am giving in that way. So can you remember that Y equal to G plus minus JB? Can you remember from the circuit standpoint that admittance equal to conductance plus susceptance? That is the thing. So that's why I gave that name from here. After converting into rectangular form, real part is GOC, which is the GOC is the conductance and BM is the susceptance, imaginary part. And I put minus sign because there is minus angle definitely you will be getting the minus here after converting. Therefore, what is that? Now your goal is to find out this and this, and the first part, GOC is actually 1 over RC. And what is that second part? This one. This is 1 over XM. So this means your GOC equal to 1 over RC. So because you are getting a number here, real number, so you are getting RC. So you are done with this one. Similarly, this one, your BM equals to 1 over XM. Because you know this value, or whatever the number is, you are getting the XM from there. So you are done. Could you follow me, everybody?
Yes.
Yeah. So this means from the open circuit test, you will be getting these 3 reading: open circuit power, open circuit current, open circuit voltage. Then directly apply this one. And to get the theta, also use that phi equal to VI cos theta. And then manipulate, calculate. So this is in polar form, convert into rectangular form. And then G 1 over RC, conductance equal to 1 over RC from the circuit standpoint. Susceptance is 1 over reactance. Here it was reactance. And that was your goal. So this means that, so that is the question. So I will be asking you this question in the midterm exam, final exam. What parameters can be obtained from open circuit test? The simple question, you will be answering that. Sorry, did you say anything? Okay, I'm sorry. So I will be asking the question, what are the parameters that can be obtained from open circuit test? So you will be answering RC and XM. And then what are the parameters that can be obtained from short circuit test? That time you will be answering 4 parameters: R1, R2, X1, X2. So in that way, with the help of these 2 tests, you can find out all 6 parameters of the equivalent circuit. And you see, because we are doing open circuit test, and with the help of open circuit test, we found out these 2 parameters. So that's, and this branch, this portion is related to the core loss component, magnetizing branch component. So open circuit test will give you core loss. This means that POC reading, the value that you are getting from the wattmeter, that is directly the core loss amount. From the previous experiment, short circuit test, the wattmeter reading, that is directly the copper loss. That is the reason I wrote there. So I'm taking there. Everybody say, open circuit test provides core loss. Short circuit test provide copper loss. Easily you can guess, because it was short circuit, I made secondary shorted. And short circuit means related to the current. Open circuit means there is no current on the secondary, and it is related to voltage. Therefore, with the help of open circuit test, you will get core loss, and which is a constant loss. And with the help of short circuit test, you will be getting copper loss. So in the FE exam, you might face this question, exactly this thing. You will be asking, what are the losses, or how can you get core loss and copper loss? Then simply answer, with the help of open circuit test, I will get core loss. With the help of short circuit test, I will get copper loss. And same thing, you will apply this conclusion in the numerical problem solving. And then also, those 2 tests are helping me, you see, those 2 tests are needed to calculate the equivalent circuit parameters. This means those 6 parameters. Now, with the help of this knowledge that you have learned so far, now I want to show you a numerical example. Then you will get fun. So everybody, once again, read this problem. Consider a 15 kVA 7500/480 volt 60 hertz distribution transformer. Assume that the open circuit and short circuit tests were performed on the primary side and that the following data were obtained. See exactly the way I explained. From open circuit test, you got these three ratings: VOC, IOC, POC. Short circuit test on primary, you got these three ratings. Now, based on these data, sorry, determine the parameters of the approximate equivalent circuit referred to the primary side. I mean, it is telling referred to the primary side because you remember when I was deriving the equations or parameters, I moved the R2 and XO from secondary side to the primary side. That's why I multiplied A square R2, A square X2. That is the meaning. Okay, so therefore this is the problem I have taken from the book example. And then if you all understand this problem, then again soon by today, I am going to assign you the second set of homework based on the transformer. You all will be able to solve. So therefore everybody now see carefully. So here is the solution. First I want to calculate that RC and XM, the core loss component. This means first I am taking the reading from the open circuit test. So everybody remembered these three were the open circuit reading, VOC, IOC and POC value. So therefore first I am calculating that power factor cos theta OC. The way I should do POC over this one. You look and then clearly written it is lagging. So therefore from here you will be getting that angle or directly it is the cos inverse value. Therefore the excitation admittance, you see, just now I discussed OAC, IOC over VOC and minus sign to indicate the lagging. And you just put those reading I over V. You look I over V, V was 7500, I was 0.2006. You see this reading. Exactly I am using these numbers. And then as I told you, you got this is real part, this is imaginary part. And you see symbol S is written. What is that one? Siemens. It is the Siemens unit of Y admittance. So therefore I just told this part is 1 over RC and this part is 1 over XM. So then you are easily getting, you see, everybody see, this means RC is 1 over that number. So I got 312.5 kilo ohm. And then see, XM is 1 over that number, 37.3. Everybody, do you understand? Like from here previous, we calculated YOC. And after converting polarity to rectangular, I got this format. And this portion is 1 over RC. This portion is 1 over XM. So this means RC is 1 over this one. XM is 1 over this number. That is the thing being done here. Everybody is fine with the calculation?
Yeah, looks good.
Yeah. Then now utilize the short circuit data. So you are done with this data. Now you come back this set, short circuit test data. So therefore, with the help of these three data, you will be finding out R1, R2, X1, X2. That is your goal. So therefore, now look that one. Look this calculation. Everybody see. So therefore, again, the power factor during the short circuit test. This equation, and I am using those three values for short circuit test. I got 0.41. And now what I would do, this time I will find out that equivalent impedance, G equivalent, which is GSC. You know, I was showing you this thing during short circuit test. And then again, you got this number and this number. So this means that your first number is R equivalent. Your second number is X equivalent. But you see that what is the R equivalent? R equivalent was, as I was explaining you, R equivalent was R1 plus A square R2. So, and then I said for a well-designed transformer, R1 equals to A square R2, which is R equivalent over 2. That thing I asked you. Here in the book, they are using a different symbol, which is like R2 prime. This equal to this equal to this. So therefore, what is your R equivalent value? This number, 75. So 75 over 2. So you got R1 value 37.5. Now, if you know the a turn ratio of the transformer, then you can easily find out the R2. Therefore, look that up. Sorry, here. Everybody say, I am calculating the turn ratio, V1 over V2, 7500 over 480. That was given in the problem. So my A value is this. So therefore, look that on. R2 is R2 prime over this. What is R2 prime? Which was that R equivalent, 37.5. And then this number is squared, turn ratio. So I got 0.154. Similarly, now you come back for x1. x1 equal to a square x2, which is x equivalent over 2. This value 166.93 or x equivalent value. You see, this on your x equivalent value that you calculated. So that thing you are now putting here. So you got x1 value 83.46. And then how to get the x2 value? So again, from here. So you are dividing by turn ratio square. This is the same turn ratio. You got this number. So then you all are done. You got x1, x2, you got R2, and then previously you got that R1 value. So you got all 4 values here, and you got the 2 component RC and XM. So you all are set. You got all those 6 parameters. Everybody is fine?
Yes, sir.
Yeah. So therefore, once again, like after the class, because this has been already uploaded and I will be uploading the video, then once again you look, you understand the problem, and then after understanding these things, then you jump into the homework that I am going to assign you today. So therefore, hopefully by the end of today, first I will be uploading on eCoursera, and then I am going to send out an email that I have posted the homework to. Therefore, you will be noticing again several problems about the transformer. In the previous class, we discussed few problems, and today we are looking, so then you will be fine. Now, moving forward, let me a little bit zoom in. How to calculate transformer efficiency? So you all know the basic definition of efficiency for any device or for any machine. It is the ratio of output to the input taken as a percentage. So what is the output and then what is the input? Input means output plus losses. So this means that in case of a transformer, if you know the output and if you know the losses, then you can calculate the efficiency. So therefore think that this losses means this loss information you will be getting from those 2 tests, short circuit test, open circuit test. So as we discussed before, short circuit test will give you the copper loss, which is the variable loss. Open circuit test will give you the core loss. So then from the reading you are getting that one. And output is what is the rating of the transformer in terms of MVA or KVA, and then power factor will be given. You can easily do that. So we will be looking one example soon. And here another term which is called the voltage regulation. Now you know that in case of transformer, you have to connect the load at the secondary side because the customers will be connected to the secondary side of the transformer. Now the thing is that you started a transformer has started operating, and then the loads were connected. Now once the loads will be connected, depending on the type of the loads, that customers are using, there will be some voltage drop. I mean, what is the power factor of the loads people are using? Depending on that, there will be some voltage drop. So that's why there is one factor voltage regulation, no load voltage. This means transformer were operating, but no customers were connected. At that time, what was the voltage available at the secondary terminal? That is the no load voltage. And once customers were connected, this means they are consuming power, they are consuming load. So therefore, there will be some voltage drop, which is called the full load voltage. And then taken as a percentage of the full load voltage, this factor, this number is called voltage regulation. So therefore, it is the expectation, it is expected that this voltage regulation value will not be that high, like not more than 5% or 10%. This means if there is huge gap, if there is huge difference between no load voltage and full load voltage, this means that voltage regulation value is poor, we can say. It is not a acceptable value. So that's why this voltage regulation number should be lower. Then that is the like pretty good system. So when you will get very high value of voltage regulation, which I am telling like poor voltage regulation, like customers are using such a load that is mostly lagging, low lagging, that has low lagging power factor. And if it has low lagging power factor, then there will be huge voltage drop. So therefore you will get huge difference here. And that is not good for the system. So that's why in the numerical problem, we will be calculating that efficiency as well as that voltage regulation. So therefore, I will just show you one example. So how to calculate that, especially the efficiency. We will not be solving that problem, just I will be discussing, and then you can try at your home this one. Everybody see another example. Consider a 100 kVA 7200/240 volt 60 Hz transformer. Assume that the open circuit and short circuit tests were performed on the transformer and that the following data were obtained. Again, similar to the previous problem, you got two sets of data from the open circuit, short circuit. Now, problem says also assume that the transformer operates at full load with a 0.90 lagging power factor. If the given power factor belongs to the load, not to the transformer, as I told you, that power factor actually related to the customers, related to the load, not for the transformer. That is the meaning. Then determine the following. What's the question? Find out the equivalent impedance, resistance, and reactance of the transformer. All refer to the primary side. So therefore, this question number A, is exactly the same to the previous problem that we just discussed few minutes back. And then question number B, what is the total losses, including the copper and core losses as full load? And question number C, what's the efficiency of the transformer? So therefore, first part, you know how to do that, equivalent impedance, resistance, reactance. Exactly, you will be following the methods that I discussed in the previous problem. You will be using these three ratings. Now, for part B, what is the total losses? That includes copper core losses. You will be just summing up these two readings. You know, this is the wattmeter reading for open circuit test, meaning that 425 is the core loss. That's why once again I have written open circuit test provide core loss. This means directly you will be taking this reading as open circuit, sorry, the core loss value. And this reading, PSA, short circuit provides copper loss. This reading 1420 watt, this is directly the copper loss value. So therefore, to answer to question number B, total losses including the copper and coal losses will full load, you will just sum up these two numbers. That's all. You are done. Now, question number C, efficiency of the transformer. Now, everybody see, what was the definition of the efficiency? output over output plus losses. So what are the losses? Losses is the sum of this number and this number. This is your losses, this value. What is the output value? Output value, you look the transformer rating on the top very first line, 100 kVA, 100 kVA. But you need, this is in volt ampere. I mean, this is in kVA, but you have to convert into watt. So that's why you see the load power factors are given, which is 0.90 lagging power factor. If you just multiply this number with this one, then that will be your watt. I mean, in terms of kilowatt, just to multiply 100 kVA by 0.9. So like 90 kilowatt. That is your output. So that thing will go in the numerator, and in the denominator, again that watt value plus those two losses value. And if you do that, you will be getting the efficiency. I mean, right now you can test. Probably you will be getting close to 98% value, efficiency value. Could you follow me, everybody? What I am explaining?
Yeah.
Great. I mean, I did not provide the solution, just I am discussing, but it's very similar. The first part, only the B part and C part is the new, but B part is pretty straightforward. Total losses, short circuit loss, and open circuit loss. I mean, copper loss plus core loss, and efficiency. Just use this equation. Then you will be fully fine. Now, moving forward, I will be discussing a little bit more, another 5-10 minutes, then you are ready to go. Transformer type, yeah. I mean, so far we discussed the working principle of transformer. We understood its equivalent circuit. We discussed how to conduct short circuit test, open circuit test, how to find out the parameters, etc. And now, what are the types of transformer? So in this book, and if you see any literature or any other power network book, you will be finding there are several type of transformer. So one is called core type, other one is called cell type. So I am showing you the diagram, then you will understand. Other type is called instrument transformer. An instrument transformer has two types. One is called current transformer, briefly it is called CT, and other one is called the PT, potential or voltage transformer. So in power industry, like if you visit MLJW and if you talk with an engineer over there, they just use CT, PT. They even don't tell this thing current transformer, potential voltage. I mean, this CT and PT are like so common and widely used, that abbreviated form of these two transformers, that even real engineers, they don't want to tell current, or they just say CT and PT. And these two are, very, very important. You see, it is both are called the instrument transformer. So, I mean, just I'm showing you the picture, but first understand like where to use. I think by the name you can understand why it is called current transformer, why it is called voltage transformer. Like you see, think about the high voltage line. For example, 11,000 voltage line or higher voltage line, 33 kV line, or even like several hundred kV voltage line. So how would you measure the voltage there? And how would you measure the current there? Like in the laboratory, in the labs or experiments, typically you use like 10 ampere rated of ammeter or 50 or hardly 30 ampere. And the voltage value is maximum 120 volt for a single phase system. For a 3-phase system, line to line is 208 volt. So that is inside the lab, or when you are doing some experiment, or you are making an electronic or electrical circuit. But what I am asking, how you will measure the voltage and current along that high voltage lines. will you use those ammeters, voltmeters that you use in the laboratory? If everybody, do you understand my question? Yeah. So I am asking how you could measure the voltage and current along the high voltage line, transmission line and distribution line. I mean, outside your home on those lines, how would you measure? Will you use your general or typical voltmeter ammeter that you use in the laboratory? The answer is no, because those are dual. Yes, sorry. Okay. So what I am saying that you can't use.
Transformer?
Sorry.
Don't you use a current transformer?
Yeah. So that is the answer, that those, I mean, in the lab that you'll be doing or that you have done so far, those voltmeter ammeter could measure only the small current and small voltage. Like in case of voltage up to, as I said, for three-phase system, 208 volt, or for current maximum 30 ampere or 15 ampere. You have not seen more than that even in the electrical circuit experiment or electronic experiment. But in the high voltage line, as I told you, the smallest high voltage is like 33 kV, 66 kV. So definitely you cannot use those. So you have to use some sort of transformer. So that's why current transformer CT is used to measure the high current along the line. Now I will show you the picture how to do that. And to measure the high voltage, you have to use the PT. This means with the help of the transformer, you can measure the high current and the high voltage. So I am showing you that thing soon. And then another type of transformer is called auto transformer. Auto transformer, this is pretty interesting. Auto transformer means it will have only one coil. It does not have two coils like primary and secondary. It will have only one coil. Portion of the coil will be treated as primary and the remaining portion will be treated as the secondary. This is pretty interesting. I mean, I will be showing. And then we will be discussing three-phase transformer. So far, we all looked, that is the single-phase transformer. And then in real practice, actual big transformers, which are placed on the transmission distribution lines, those all are the three-phase. And then because it is three-phase, every analysis, every equation, everything is the same that you have learned in the previous chapter, three-phase circuit. It will have delta, it will have Y, and all the equations equally valid for the three-phase transformer. So we'll be discussing. And then the other two type is called the leakage transformer, resonant transformer. We will not be covering these things, just I am telling you the name. Typically, these are used in some electronic circuit or the communication circuits. So therefore, moving forward, I think we don't have much time. I just want to show you this one and then I will end up today. Core type of transformer and then cell type. You see the definition. Core type means made up of unlaminated silicon steel structure. Actually, those magnetic material or core material, they are laminated silicon steel structure type, and it produces large leakage or cell flux and less mutual flux. And cell type, it is made up of two laminated silicon steel structure. This means it has two separate magnetic core material, and it produces less leakage or cell flux and large mutual flux. And this type is more efficient but costly in material. So that's for this core type, cell type. I mean, just in a minute, I will show you the diagram and then you will be done for today. Yeah. So the core type is the one that we have discussed so far. So So this is the one that we have discussed so far. So this is called that core type. And then there is other structure, you see, I'm showing it here. And then you have another structure. Okay, so you see, secondary coil is here, and this is the primary coil. So this is called the cell type. So this means that the core type is, it has only one magnetic material. And then the coils are placed in this fashion. This means these coils are placed on the same material. Coil does not have direct linkage. They are not bonded together. They are magnetically coupled, but only one material. On the other hand, for the cell type, you see, you have two separate material, this type of material. On which there is primary coil, on the other there is secondary coil. Now it has relative advantage, disadvantages. So what is the advantage here? That it is somewhat less expensive because it has only one magnetic material. So then easily you can understand. It is expensive because it has two magnetic material. I mean, you can argue that, okay, the size of one magnetic material could be smaller than this one. That is true, but still you need to separate things. So therefore, typically it is expensive. But as you noticed in the slide that I was showing you, this system is more efficient and like much more popular than this system. Although many manufacturing company and many power network uses this one. So kind of all over the world, 50-50. In some power company uses this one, some power company uses this one. Now for this one, what happened, like, so you all know that once you apply the voltage and then the flux is created. So this is the flux. So this is that flux, and flux is mutual. But initially, once you apply the current or the voltage and then current flows through it, there is one local flux which moves around here only, which is this on this pion. So this pion is called the self or the leakage flux. And this actual phi, which links to secondary coil, this is called the mutual flux. This phi is called mutual because it is common to both primary, secondary. But there is another flux which just moves here, which is local. It is called the self, or it is also called the leakage. So in this case, what happens? In this case, the amount of self or leakage flux is higher than the mutual flux. In this case, what happens? Similarly, you apply voltage, you apply current, and then there will be one local flux here, which is that this pion. And then there will be mutual flux, which is going here. And from here, from here also, there will be one local flux, which is this phi 2 cell flux. But then there will be another flux, which is going. So for example, this is phi over 2 that is coming from here, and that is coming from this coil, which is phi over 2. Therefore, if you sum up phi plus 2, phi plus 2, total flux is phi. So in this case, this is the mutual flux, sum of this coil and this coil flux. In this case, the mutual flux is much higher than the cell fluxes. So because it has much higher flux, so that's why some company or some manufacturer prefers this type. In this case, mutual flux is less than the cell flux. For this type of core type of transformer, most of the flux goes as the leakage or the cell flux. there is less amount of mutual. In this case, less amount of cell flux but large amount of mutual flux. So based on that fact, some company prefers this cell type, some company prefers this one. But as I told, I have noticed like over the literature and after joining many conferences, like kind of 50-50, like all over the world. Some prefers this one, some prefers this one. But definitely this one somewhat expensive because of having the true magnetic material. Everybody, could you follow me?
Yep, sounds good.
Okay. So therefore, I think already it is 11:30, so I don't want to go much. So okay, then hold on there. So in next class, then I will be explaining these things: instrument transformer, auto transformer, in next class. And at this point, then I'm stop sharing.